Yeah, good afternoon, ladies and gentlemen. Today I will be presenting work that is being conducted at the Computer Vision and Remote Sensing Research Group in Berlin. And I've selected this topic because I want to give you an overview on several research projects we are following in Berlin on the one hand, and I also want to have the opportunity to focus into some details and some work we are planning to do in the nearest future. And I hope that in that way I can both give you an overview about the diversity of the research we are conducting and an insight into detailed research projects we are currently following. The work I'm presenting here is done in cooperation with 5 PhD students and postdocs in the groups. That's Cornelius Wefelscheid, Tilman Wekel, both being PhD students in close-range reconstruction from images, and Stéphane Guillazo and Olivier Dont being postdocs and working on synthetic aperture radar, and Esteban Aguilera finalizing his PhD thesis in cooperation with DLR and Dr. Andreas Reiper in Munich, next to Munich actually. Okay, then let's get started. First, I want to say a couple of things regarding the research group itself. We are having 3 major focus points in research. One is synthetic 3D surface reconstruction from images. The second one is synthetic aperture radar remote sensing, and that's quite far apart from each other. No? We are taking a camera, making images, do 3D reconstruction from the images, and the radar is a microwave technology and an antenna sitting on an airplane or a satellite even, and making larger images with a lower resolution. So there seems to be quite a distance between those 2 areas, and we are trying to understand both of these data sources, extracting objects from them or doing 3D reconstruction in both areas. And that's so in that sense the focus point image analysis is uniting these 2 other emphasis. No? However, we have always been doing some work in medical applications, medical image processing, and that's usually rather belonging to the image analysis group. No? These few points show those efforts in medical image processing. For instance, we have been several years ago been working on position-accurate superimposition on head-mounted displays. There we've developed something that looked like that. A person is wearing a screen in front of the eyes. That's a see-through screen. And we strive to superimpose invisible information positionally accurate. For that purpose, we have to determine both where the eye is positioned with respect to the screen and where the whole frame is located in the overall world. And that requires a couple of coordinate transformations, and then you can, for instance, superimpose objects that are, for instance, in the human body, like the veins and arteries in the liver in that case. No? But that's not the focus of today's talk, so let me just continue fast. The first area is 3D reconstruction from images, and in order to get an impression of what is done in that area, we have outlined the processing flow, but I rather want to show you an example because that's faster. We are acquiring images, for instance, from such a Segway with the camera mounted on it, then from the images, feature points are extracted and matched or tracked over the image sequence. And from that, we are determining the positions of the cameras in space and reconstruct a dense surface reconstruction of the objects, for instance, of that wall. And that's being shown in the area. That's done in many research groups, and also we are able to do that. And on the basis of such a processing tool chain, from images to sensor passes to dense reconstructions of walls, we are starting with the research work, actually. I'm supposed to close this here. Yeah, all right. So somewhere on the end, at the end, we have a 3D model. And in between, we have to find the camera positions and the orientations of the sensor. And that's, to some degree, a research issue. And there is where I want to start with some current research. No? So what is quite the task is that you're having the cameras and you want to have the orientation of several cameras in a sequence. You want to find how a second camera has been moved in comparison to a first one, and you do that by finding the intersection of corresponding rays. No? Then you're determining how far the second camera is translated and how it is rotated until you get proper intersections. When you're joining a third camera into that, then you usually have the problem that the scale of the first image pair is not transferred to the second one. Therefore, it's quite advantageous to do the relative orientation of an image triplet, taking 3 images, then you're finding you're setting the scale by fixing the distance of the first 2 cameras with respect to each other, and then you're transferring the scale by positioning the third camera accurately with respect to that first pair. And if you keep on going like that, then you can take the first triplet that determines the baseline between the second and the third camera, take the second triplet, and make the second baseline as large as the first one in the second pair. And so you can transfer the scale from one triplet to the other, and that keeps your whole processing chain more stable. No? So we have a setup that we are getting several image frames, and the question is now, how do we join them in triplets? If you have been moving the cameras, and the most natural thing is that you're taking subsequent triplets in order to organize those triplets. But that's not necessarily the best way to how to process the data, because when you want to acquire a 3D object, then you may be moving the camera to different sites, and on the path you're looking on the objects several times. No? So you're repetitively seeing the same thing, and then you go back and forth, and the question is, how is the connection between all your images? No? So
this figure, these red one are the images, the red circles are images?
The red circles are images, exactly, and the green ones are triplets, and we are building such a graph structure. No? And whenever you are repetitively looking at the same region, then you have an image index that's fairly high, and you join them with low index frames to a common triplet. And that gives you a graph structure that is indicated in an example over here. And what we are trying to do is we are finding something like a minimum spanning tree in that graph structure in order to identify the most central triplet with which we are starting to find the relative orientations of the cameras with respect to each other. And that allows us to keep the the branches in the tree structure short. The advantage of that is that the errors that are added up by chaining triplets are not becoming particularly large because the number of chaining operations is low. If we would have been started at the beginning of the sequence and just chain one triplet after the other, then until the very end of the sequence, there's a long distance, and all these relative orientation errors may add up to become a large error. When you're finding the most central triplet, then the branches in the tree are fairly short, and the errors are not that large. No? So after orienting the image triplets in that way, we have a much a solution that's much closer to an optimum than by processing them in a sequence. Yes, please.
So in that graph, how are you defining the relationship between two different triplets? Like the number of frames in common, or do you have some other features to the
Yeah, there's always a branch, an edge between two triplets when two of the images are the same, no? And the third one is a different one.
And how is it directed? Like in the upper graph, I see like there are arrows, so it means like one person. Like what is the direction?
Yeah, it's not. That's how it's plotted in this graph. It's basically undirected because you have an arrow in both directions. No? Okay, and then there is also the task of finding loops in the structure. No? Sometimes it's not possible to establish a triplet itself, but you have to find out that you are seeing the same thing. And that is, for instance, solved with vocabulary search tree technologies on the features extracted from the images. And we are actually doing it slightly differently by computing a descriptor variance similarity. We are, for instance, extracting image features like SIFT feature points. Those are described by a lengthy feature vector. And we are computing the variances of the elements in the feature vector and compare those variance vectors among images. And when they are fairly similar, that also is indicating that we are looking at the same thing. No? And with such a matrix of descriptor variance similarities, we can identify loops in the imagery. No? Here, for instance, you see an image sequence that basically shows a camera circling an object several times, and when you go along the row, you can see that here and there the same objects are visible, so it's basically two circles around an object shown in this matrix. No? And with that, we can then set up relationships in between the images in order to make sure that the orientations of the cameras are determined correctly. Then, after that, a bundle adjustment is conducted that gives us an optimum solution. And that's usually done by all these approaches that are evaluating image sequences. First, you're finding initial solutions by chaining relative orientations with respect to each other. Then you are suffering from the random errors of relative orientations, and you want to come out with an optimum solution at the end, and that is what you obtain by a sparse bundle adjustment usually. No? And the closer you are to that optimum solution, the more easily or the more reliably you are getting the optimum solution and don't get stuck in a local optimum. Well, that's basically the art of processing. And these two steps of analyzing the graph structure of the triplets and finding the loop closures help us to get an initial solution prior to the bundle adjustment in order to find that optimum. If we are not taking that into account, then after lengthy image sequences, it may happen that at the end you're coming back, look at the same thing, and in your evaluation it is considered being two separate things, and you're basically, well, you're walking around a house and you have 2 times the first wall, and it's actually not the same object. No? And that's what we want to avoid with that technology. When the bundle adjustment is conducted, very often techniques like sparse bundle adjustment software package is applied, or small sparse bundle adjustment, SSBA or SBA. But we have developed our own software system for that purpose. And the feature, the advantage of that is we have developed a system that is applicable to any kind of problem where you're having a relationship between measurements on the one hand and unknowns you want to determine with help of these measurements. No? So if you can set up observation equations with measurements as a function of unknowns or conditions as a function of several of the unknowns, then you can use our software system, and that's being provided on GitHub as an open source software system, and we are making use of computations on graphics cards with it. And we are also using software for sparse matrix computations. So that's actually giving you the chance to compute your problems fast, making use of modern graphics cards, and not having to learn much about GPU programming. You know? So that's quite...
So you're, in this one, you're doing the non-linear least squares.
Yeah, that's right.
So the widely used method is called Levenberg-Marquardt, the method, and that probably there in MATLAB. Is your method similar to that, or what is the method you use to do this optimization?
Yeah, the Levenberg-Marquardt optimization is used inside of it in order to find the solution, or gradient descent as an...
So this is just the fast implementation on GPUs to make it easy for people to use?
Yeah, so to make it easy for people who do not want to get into graphics card programming. No?
So what is OF? OF means open OF?
Open Optimization Framework.
Oh.
Yeah. So it's not, it's referring to something a little more general than linear least squares, but that may need to become an extension on top of that. Yeah, well, what this graph is indicating is that we are not only evaluating images where we have bundles of rays from observed image points to unknown 3D locations of object points, but we are combining it with, for instance, radar antennas that are rather observing distances towards the unknowns. No? So as opposed to the quite specific sparse bundle adjustment, we can introduce any kind of observation equation. Of course, it does not necessarily need to be geometric. It's just applicable, as I said, to any kind of functional relationship between measurements and unknowns. Yes, okay. Then this is actually the historic alternative to using images, and it's basically interesting not only from the point of view that once we are using cameras, we can avoid the danger of having to climb on walls or so of houses or buildings or any objects we want to acquire. But the more interesting thing is actually the kind of way humans have been perceiving the objects and how they made sure that they acquire the geometry of objects completely with few measurements, actually. No? You can imagine when you're climbing on a house, then you cannot do many measurements, but you rather have to do a few only, like acquiring the width of the wall or the height of the wall, which is 2 measurements. And in comparison, our modern cameras have megapixels, and that would basically mean we have millions of measurements for such a wall. No? That's a significant difference between historic measurement technologies and modern ones. No? And do you know why actually historic techniques were successful despite the fact that it's doing only a few measurements?
You can tell us.
Yeah, yeah. It's maybe too simple for you to answer such a question. Yeah, right. You already have a model when you get started. Of course, you see that this is one planar wall being limited by certain edges and so on. And the human is starting with that knowledge. And what we are actually striving for in 3D reconstruction is to acquire that knowledge from the measurements made by these millions of pixels. And it's important for a certain reason. No? It is important because the measurements we are doing on the pixel basis, they are kind of noisy still also. And despite the fact that we have millions of measurements, they are not absolutely accurate, and they become or maybe made accurate by introducing the modeling knowledge. No? So if we know that we are watching a planar wall, then we can actually make all the points that are sitting on the wall being located on one plane mathematically, strictly, and that makes all the evaluation much more accurate. And that is something we have to impose on the 3D reconstruction technology I've just shown. No? If you remember in my video, the wall was kind of precise, or on my first slide also the edge of the roof was kind of accurate, but not exactly. No? It looks like it's wobbling back and forth, the roof is melting or so, and that's limiting the accuracy, and the deficit is not to be overcome by improving the sensing technology. Of course, we can strive to do that, but we would have a much easier time by an intelligent analysis of the data. And so we actually have to come closer to what this guy had in mind when he was climbing up and doing his 2 measurements, the width and the height. That's what we are also trying to do. So in stereo, you take 2 cameras and then you intersect the rays and you have a 3D reconstruction. However, we can also at some occasions infer 3D structure from single images even. What do you see here on the left side? A cube, right? And I have to let you know you are wrong. This is a plane. However, of course, everybody among us is seeing a cube, no? Because that's the simplest interpretation. Just according to Occam's razor, we are coming up with that simple interpretation. No? Or if we are considering how is a camera looking onto an object and we are able to identify a rectangle in the image, no? Then we can interpret the lines of the visible quadrangle as a rectangle, and that would allow us to compute orientation of the camera with respect to the rectangle. No? From which direction does the camera look onto the rectangle, and in which way is the major ray of the camera inclined with respect to the plane spanned by the rectangle. No? Then we have some 3D information already. No? That's one of our research we have been trying to do. No? So that's a thing. What do we perceive? What is there in reality? Is what we perceive actually there in reality? And are we then able to come up with some 3D measures from the things we are actually seeing 2D only? No? That's another aspect of the work we are trying to follow. Let us rather have a look to the evaluation of the point clouds. No? Well, what is output of the reconstruction from my video is the point cloud, and we can mesh them. So it's maybe a triangle meshed point cloud. No? That's the surfaces. Then we may want to simplify it, store less points than we actually measure, because it's not necessary to store millions of points on a plane. We can segment it in order to find how an object is constituted by a polyhedron, for instance. Oh? And I'm usually calling that we are searching for geometric primitives. No? We are not trying to find out that we are looking at a table, but we are analyzing the point cloud, and we are finding that it's a plane and several planes, or a cylinder, or a smooth curved surface, and edges in between smooth surfaces. And so at this point in the research, we are trying to find geometric primitives. No? Then we may fit models, and when we have fitted the models, we are able to recognize what we are looking at from the 3D data. No? So, of course, you may recognize objects by looking at the 2D images itself, no? But this is just research directed towards analyzing the geometry of point clouds coming out of a stereo reconstruction. And a first investigation we made was analyzing the description length of point clouds when it's being combined with a model. First, we need to come up with an agreement of what the data is on the one hand and what the model is on the other hand, and how we are describing the data given the model, and then we are describing that with lengths. No? So the description length of the data is the sum of the description length of the data given the model plus the description length of the model. Now imagine you are having a cloud of triangles, for instance, of coming out of a Delaunay triangulation. Well, that's your data, and you can look at the coordinates of those points, and that describes that has a certain amount of information coming with it having a length. Then we wouldn't have a model at all. No? However, we can also fit a certain model to it, and then only describe the data by the deviations from that model. So if we are looking at a cylinder, then we are fitting the cylinder, and we are not describing the full geometry of the triangles, but just the differences between the cylinder and the triangles. No? Then that's the length of the description of a cylinder plus these little differences, no? Giving us the overall description length. No? And what we did is, our model is not a cylinder being fitted to the point cloud, but we say the model is triangles also, but it's not as dense as the data triangles, because we have been leaving out the unnecessary points and have larger triangles. No? So the question is, how do we then describe the data? Of course, we have the larger model triangles and the smaller data triangles, and we have those few model triangles and the differences towards the data triangles. No? That's these two terms, the data triangles given the model and the length of the model. If we have few triangles in the model, then that's short, and this needs to be long because there's a lot of differences between the few model triangles and the many data triangles. No? In the extreme, we are basically not having any model triangles, and we only have data triangles, and we have to describe all the triangles with the full coordinates. No? On the other end, we may say that all the triangles are belonging to the model, then they are directly describing the data, and this becomes zero. No? So there's two opposing ends, no? And those ends are basically equally long, and when we are then either expanding the model length or we are decreasing the model length, we are getting two curves. No? The one curve, you may not see that clearly, is describing the model, getting an ever longer length. And on the other hand, that's this blue curve, we have the green dotted curve, the data having ever fewer, an ever shorter length. No? And both curves added give us the overall description length at a certain time. And there's a minimum in the middle when we have something like the model triangles fairly well approximating the data triangles, well, in optimum describing them perfectly, but leaving out a lot of the data triangles.
So what is the model? You have like a cylinder as a model? Or?
No, that's what I mean. We are calling the model a less dense set of triangles. No? And then what we have been observing is that the model belonging to this lowest point in the curve, that's something remarkable. And that's on the next slide. No? This is an example starting with all the little triangles and making it less dense. And actually, when we are approximately here, that's at the bottom of the curve. No? So the minimum description length is actually the situation when really large triangles approximate the many triangles almost perfectly. No? In this way, we have a mathematical method that is actually able to find the shortest model also that's describing the object perfectly. No? Of course, the shortest model would be not having any large triangle. That's not what I mean. The shortest model we are looking for is that model that is describing the surface perfectly. No? Of course, that has something to do with the sensing technology. If it's noisy, then the triangles wobble back and forth more than when it's not that noisy. But still, we have the impression, and that's the message of this work, that we are able to identify the model that perfectly fits the data in a situation where we are just smoothing away the sensing noise and not the object details. That's just an investigation we made in order to see what's happening when we are working with minimum description length. We do not really use that in order to do object reconstructions. That's rather a mathematical thing. And now I will be talking about a project that's trying to find the real reconstruction. There we are subdividing between smooth parts and the edges. And we are subdividing the surface into patches. And then such a patch can be subdivided separately from the others. And we are using the smooth parts and the convex edges and the concave edges. And that's what we are doing, analyzing with the help of a Voronoi-Based diagram, actually. The Voronoi diagram helps us to identify the skeleton along the edges of a model. No? So when you're looking at this 3D model like that, then the Voronoi diagram of the triangle sitting on the edge helps us to find the skeleton line, and then we can find the skeleton along those edges and find the intersections and then the smooth parts, and that gives us the overall 3D model. That's another work, and we have been analyzing how the method conducts when we are working with noisy data, and we have compared the method with competitive methods of Casals and Yoshizawa. And actually, when you look at it, how the other methods perform with respect to the convex and the concave skeleton parts, and actually it looks like our method performs quite well. So that's on the visual side, and here we have made the analysis with help of the graphs of the false positive rate versus the true positives. And the red curve shows the results from our method, and it's apparently a little better than the competitor methods. I have to go through all this a little faster because I want to show you something with respect to our work on synthetic aperture radar technology. Yeah,
this is interesting.
Yeah. And that's used, for instance, in order to analyze for deformations or do 3D reconstructions also. And in order to explain some of the work, I have to explain what the radar does in the first place. No? And the synthetic aperture radar uses a short antenna and makes it synthetically long. No? The short antenna is irradiating beams in a wide angle, and then we are actually getting a low-resolution image of the world because the wide beam is not able to differentiate between different locations. Because the echo, the response of the impulses that are sent by the antenna cannot separate between objects because the beam is so wide. No? Now the antenna is flown past the object, and you are collecting many of those beams, and that is basically giving us a frequency modulated signal while passing by an object. And as we can compute the theoretical response of a single point in space, we can basically compute a correlation computation between the observed response from the object surface, that's symbolized here, and the theoretic response of a point. This is a simulated example, and it shows a single point in space only. No? So we are correlating the response of the point with the reference function and conduct a matched filtering operation. And here you can see the output of such a correlation operation, and the lengthy impulse being equivalent to the response of the widely open beam becomes a slim response in the matched filtering output. No? So the matched filtering operation is basically making the originally widely open radar beam quite focused, and that allows to differentiate between details in the image. No? And when you don't do that in such a principal sketch, but rather in a practical data set, then this is the raw data from received by the widely open real antenna, and that's the output of a matched filtering operation in range direction, in range direction with respect to the antenna, and if you also do that in flight direction, then you get that high-resolution image. No? That is actually necessary in order to explain the first research project we did.
In this image, you get each pixel in this image is the distance. Is it a distance, or what is the?
Yeah, this direction basically is corresponding to the distances from the antenna. No? It's a side-looking radar system, and the near range pixel has a certain distance with it, and the far away pixel also has a certain distance. No? So it's basically an impulse sent, it's reflected, and if the reflection comes fast, then the pixel is close. If the reflection comes late, then the pixel is far away.
Is this image like considered depth image? Like you get a depth image, like a connect or something?
I wouldn't call it depth image that much because it's rather the pixel's column index is telling you something about the distance from the antenna. No? But it's not 3D, so the term depth is a little misleading. No? It's like you're projecting all your points onto one plane that's sitting on the path of motion of your antenna. Yes, please.
What does the pixel value of that image say?
That's the strength of the reflection. No? So if the object at a certain location is reflecting a lot of the microwave radiation towards the antenna, then it's bright. And if it's like a mirror reflecting all the energy away from the antenna, then it's dark, and that is shown. No? So it's basically the ability of a certain surface reflecting the microwave radiation back towards the antenna.
So can we assume that each row in that matrix is encoding both the spatial, like the XY locations of that object?
In a sense, yes. No? This direction is the distance from the flight path, and that direction is the position along the flight path where you are seeing the object. No? So the sensor is flying in this direction, and here we have the positions along that direction. No? Okay. Then synthetic aperture radar is used in order to acquire the third dimension by a technique called interferometry. Well, there you are using not only one antenna, but two antennas that you can do by flying along the terrain twice. Then you're kind of sending your impulses to the terrain surface. And from the phase differences, you can basically infer where your terrain surface is. No? That's measuring like an interferometer. The reason is that the synthetic aperture radar is doing the sensing with coherent radiation. And then that makes sure you are getting a phase with the amplitudes that are being shown in the image. No? And the phase is basically the distance minus the full wavelengths, and the rest, the rest of the distance, that's transferred to a phase value. No? So if it's 10% of a phase of a wavelength, then that's just 10% of 360 degrees in a sense. No? And that phase is stored with all the pixels. And if you compute the difference between images, between two images, then you get phase differences. No? And those phase differences are indicated in my graph by the intersections of all these circles. No? So in this area, you have a 180 degrees phase difference in that area where the circles are, where the wave peaks basically come together with the wave valleys. We have 0 degrees phase difference, no? Because we are counting on both ways in the distances, no? And now you can basically analyze neighboring pixels, and if the phase difference development is irregular, that is an indication of a deviation of the terrain surface from a plane. So you can basically compute a terrain model from those phase differences as you are analyzing all the pixels together, and as you may assume that the phase difference between neighboring pixels is always the smallest possible phase difference and not including several wavelengths. That may be different when you're having high jumps in the terrain surface, like a slope or a wall or something. But in general, it's going that way. The disadvantage of that technique is, however, that it's only able to measure the differences in the viewing direction of the sensor, certainly, no? What is another property of the technique is when you're flying the sensor twice with a certain time difference, no? Then you can not only observe something like a terrain model surface, but you may also observe whether the height of the terrain has been changing. No? Then, of course, you need to make sure that you already know the terrain model. And if in your pattern something unexpected happens, then it's not due to the fact that once up on a sudden a mountain has been occurring over here, but it's due to the fact that a part of the terrain may have shifted somewhere else. No? So you can measure landslides with help of that technology, or you can measure how the surface of a volcano moves prior to an outbreak of the volcano or something like that. However, again, as I just said, it's only measuring in the viewing direction of the sensor. So if your motion is happening parallel to the flight path, or in some way in 3D and not only away from the antenna or towards the antenna, then you either don't see it, or you need to come up with a model about your surface motion. No? For instance, you may say a glacier is usually moving downhill and the surface doesn't change, but all the details in the surface stay in the same geometry and it moves downhill only. No? Or when there's some excavation underneath of the ground, the change in the surface is vertical, and the component in the viewing direction you're observing, and from that you're inferring an equivalent vertical motion. No? And that's subject to this SAR interferometry technique. And now we have basically done an investigation that tries to infer several components of a three-dimensional motion from the data. No? And that's done. Yeah, I have to be much faster than I'm actually right now. So, yeah, right. We don't have much time left over. No? So if we are looking at the phase in the processed radar data, then it assumes that we are watching with a 90 degrees angle towards the flight direction. That means the center of the beam is in the middle the viewing direction. No? And that also means that the development of the faces in the center of the beam is horizontal. No? And when we are subdividing all the impulses sent into a forward-looking and a backward-looking part, then we can also do the matched filtering operation with the forward-looking and the backward-looking part. And then in the middle of those beams, the phase development is actually not horizontal, but it has a slope. And that results in the fact that when the surface has been moving in between the two data sets, that we are basically getting a different observation in the forward and the backward looking parts, no? Because we have kind of an error in the matching operation, and that matches to different places with respect to each other. No? So a motion would always mean we are not having congruence between pixels actually belonging together. We are not looking at this place, but at a shifted place. And due to the difference in the phase gradient in the two viewing directions, we are now able to identify that the terrain has been moving in two different directions. So that's allowing us to analyze surface motion in two different viewing directions. No? That's shown in this work, actually. And now maybe that's getting us closer to the end, and that's interesting for some among you also. That's radar tomography. We are not only flying twice across the terrain, but several times. And we are observing something like vegetation volumes, actually. No? And we can investigate this problem with help of compressive sampling technologies, such as Enrique does in this group. Is he here right now? Or Young also?
Yeah.
Maybe
the sparse.
the sparse analysis. No? The point, the interesting part of that is you may acquire a signal like an image, and that's not necessarily sparse directly, but there may be a way to transform it to something that is sparse. No? So that's actually happening when you're doing a wavelet transform on an image. No? So if you're, for instance, transforming this often shown image into wavelet coefficients, and then you may see the development of the magnitudes of the wavelet coefficients. This is showing that the low index coefficients are having the non-zero values, but even more so if you zoom into a little area over here, then you see that even for low index coefficients, only a few are having non-zero values. So that's actually a sparse representation of the image, and we can now use that in order to evaluate our data. No? So we would not work with a system where this is the unknowns we want to estimate, and those are the observations, the few observations we have. No? Then we try to estimate the numbers in a long vector from an underdetermined equation system, and we can do that because it is possible to transfer this system into such a system where there is a sparse representation of the original signal f, and then we are basically putting this matrix A times psi transpose, psi being the wavelet coefficients, into a sparse sampling analysis, and that would basically lead us to the case where we are minimizing the L1 norm of the sparse vector alpha subject to having a small difference between the observations and this part on the right side of the equation system. And that L2 norm should be smaller than an error that is due to the noise in the data. And that's what several among you are using in some kind of sparse sampling techniques. And we do that in order to investigate our radar tomography data. No? I have shown you the several flight passes, and here is the volume. No? So that's not necessarily sparse. No? There's a reflection from the ground and several reflections from the vegetation volume. Of course, there's some zeros in the air, but all these voluminous occupied elements, they do not, we cannot consider that sparse yet. No? We have to represent our data differently. And that's what we are doing by analyzing the variance covariance matrix of the radar data. No? So we are getting a transformation that's equivalent to doing a wavelet transform on an image. And then we can use sparse reconstructions. And due to the fact that I'm kind of running out of time, I'm basically showing a result here only. This is the point cloud. No? We are getting that by compressive sampling. And then we are estimating planes into the point cloud, similar to what I have been shown in the analysis of the point clouds we are obtaining from stereo reconstruction. And then I'm basically, oops. Aha, I'm not seeing well here. Back to the finish of my presentation. This is showing us a sequence of images acquired of an object for which we did a 3D reconstruction. And we are basically projecting newly acquired images onto that 3D reconstruction. That basically demonstrates that in a world of 3D reconstructions, from the images we can obtain the position where we are standing with the camera. No?
So this is not by SAR, right?
This is not by SAR, but that's back to the structure from motion technology. But there is some connections with regarding the synthetic aperture radar technology, because some of the radar satellites, they come with very high resolution orbits. No? The orbits are extremely precisely determined in the range of decimeters. For instance, the TerraSAR X sensor is sitting on board of such a satellite. And if you are basically able to identify with a subpixel accuracy where on the terrain a point is located, then you can transfer that high accuracy orbit right into that subpixel accurate point in the image. No? That basically means with help of those synthetic aperture radar satellites, we can determine locations on the Earth with a precision in the range of, let's say, decimeters. No? For instance, for such corner reflectors, that's feasible, no? Because the three sides of the reflector make sure that a very strong reflection is sent towards the radar antenna. And as we know how theoretically such a single point looks in the radar image, we can also determine very precisely which sub-pixel coordinates that point has in an image. And that allows us to determine the global position of that point very accurately, provided we know a terrain model of the terrain. And now what we have in mind is using the close-range reconstructions in order to get the response of other objects very precisely, not only corner reflectors, but very detailed surfaces, maybe walls of buildings with respect to each other. And if we know the geometry, then we can simulate a radar image, we can correlate it with the actually acquired image, and then we can say very precisely where, for instance, the corner of two walls of a house is located in the image, and we can transfer that position into global space. So the hope is basically to do that for several locations, not everywhere, because when we observe vegetation or humid soil, then that's not going to work, because electromagnetically the response cannot be predicted. But when we have reflections from houses, then that may be predictable, and we may find the positions of the points in the 3D world, and we may coordinate many close-range reconstructions in a global coordinate system. And by looking at them with cameras, we can determine the positions of the camera precisely in global 3D coordinates, for instance, or without GPS sensing technology. So that would basically be the outlook of this technology. You can imagine that it's quite a challenge, because that's how a radar data set looks. And if we have a model of Brandenburg Gate, then we would need to use that model in order to predict this data set and get the matching between the radar data and the 3D model. But as I said, hope is that we can then do positioning on the basis of images only, without GPS technology and so on. And that finalizes my talk, something like 15 minutes late. No? Sorry.